So today we're finishing up the three-part series that we had assigning point groups to molecules. So we built some molecules, went through the flow chart on Otterbein or SymOtter, and discovered the point group for each of the molecules. That allowed us to then pull up the character tables, and you have those packets of character tables. And we went through the character tables and assigned the vibrational motions. So we determined what row each of those motions was in the character table. And then today we're going to use those symmetries of those different motions, vibrations, rotations, maybe even electronic cloud things, to determine if the transition is allowed. So those are the three steps. You've got to know the point group, got to find the character table, and assign the symmetries that are involved, because this is the interaction of waves. So that's really the whole thing with quantum mechanics, is that describing nature as a wave in all of its aspects, whether it's a rotation, translation through space, vibration, the electron cloud, all of those are waves, and waves interact. You can multiply those waves times each other, and when you integrate over all space, you can determine how those waves overlap. The positive regions will enhance other positive regions when they're multiplied by each other, and if you have a positive region times a negative region, they cancel each other out. And so that's really all we're doing here, is looking at the way these waves are multiplied by each other, whether they reinforce each other or cancel each other out, will determine if light can interact with those different waves in a molecule or an atom. Okay, so today we're going to be solving several of these transition dipole moment integrals. Remember, that's the intensity piece on a spectroscopic peak. So what were the three pieces for an absorption profile? I had the acronym BIG. It's a good review, all right? Get our brains going on Monday. So A equals big. Okay, B is this B word is something that you absolutely will learn over the time, because especially if you go into thermodynamics, because he was sort of the pioneer of quantum thinking. Boltzmann, yeah, B is Boltzmann. So what does Boltzmann's factor tell us? Tells us whether there's atoms or molecules in that level. It's the thermal population piece. If there's no atoms, ions, or molecules in a particular energy state, you're not going to have an absorption peak. I mean, light might match, but there's nobody there to absorb. Okay, so the Boltzmann piece is the population. Then I is what we're doing today, the integral, the transition moment integral. And then G is the line shape, that Gaussian line shape. So we'll get to that in lab. We'll do some numerical simulations and things in lab where we put a Boltzmann distribution, a Gaussian distribution on a peak. But today we're talking about that I piece of absorption equals big. And so let's jump in. So we're down here. This is what I've just talked to you about: Lewis dot, Vesper theory, point group, character table, assign those symmetries. And now we're using the direct product tables today to look at the symmetry of those three functions multiplied by each other. Okay, so the symmetry of the total wave function is, again, more functions multiplied by each other. It's all of the wave functions, and it's the product of all of them. So this psi t is meant to represent the total wave function, and it's the electronic wave function times the vibrational wave function times the rotational wave function times any kind of translational motion. So I just have all of those little quantum numbers there, you know, N and J and V and E. And so if everything's in the ground state, the ground states are symmetric, and so the total wave function is symmetric. But if, let's say, the vibrational wave function is excited and it's asymmetric, then that changes the symmetry of the whole thing. Because remember, if evens are, it's all evens multiplied by each other, but there's one odd, then the whole thing is odd. Okay, and so then whenever we have these functions times each other, sometimes you'll see this little times in a circle. That just means the direct product. And so when dealing with a function, you have lots of numbers. It's like an array, and it's the first cell times the first cell of each function, and then the second times the second, and the third times the third. So that's what we mean by the direct product. It's just all the elements in this vector times all the elements in that vector, one times another. There's no adding. It's just cells times cells. And so we're going to use this to determine our selection rules. So that intensity is proportional to this transition dipole moment, which is this mu or dipole moment operator operating on the initial state, and then it's compared to the final state that it's trying to go to. So it's these three functions times each other. We simplify this with Dirac notation, and we see that we have just the quantum numbers here. So if we're going from state n to n prime using this dipole moment operator, this represents light. So we use symmetry to know when this transition moment integral is 0, and that the results of the direct product does not contain the totally symmetric irreducible representation. That's the long phrase. A simpler way to think of it is if it's not the top row of the character table, then this integral is 0. If the integral is 0, then the square of that integral is 0. And so we call this forbidden by symmetry. The spectral intensity is equal to 0, and we say that that transition from n to n prime is forbidden by symmetry. So this is the main point of this whole part of the course, and we will do this the whole semester, is determine if this transition or that transition is allowed or forbidden by symmetry. So I just put this big thing in your slides. It's like, let me repeat, if it doesn't contain the top row of the character table in that huge integral, and a lot of times it's a bunch of terms plus each other. So you might have E1 plus E2 plus A2 plus A1. If you see that A1, that's the top row, and that's contained inside that integral, that little piece will be allowed. Just think about when you did your calculus, you had a bunch of terms plus and minus in there. And if any one of those terms was non-zero, then the overall result was non-zero, even if all the other terms were 0. And so we call this forbidden by symmetry if it doesn't contain the top row symmetry. So let's get into using it. So we use that Vesper theory to estimate the geometry. We find the point group of the molecule using the flow chart, or by using example molecules. Like if we know the symmetry of water is C2V, and we can look at this molecule and say, well, that looks like water, then it's also C2V. We don't have to use the flow chart. We find the symmetry of the wave functions and select the symmetry of the spectroscopic interaction. So this little line here is important for you guys. For direct absorption or emission, so a photon comes in and is absorbed, or the molecule's in an excited state and drops down and spits out a photon. So just a direct interaction with a photon, either absorption or emission, the symmetry is X, Y, or Z. So we would look in the character table for X, Y, and Z, and that would be the symmetries of light. You come across to the left side of the character table and find that row. We have to know the symmetries of the light that's coming in. We also can do scattering. So for Raman and Rayleigh scattering, the symmetry is second order because it contains 2 photons. So you can think about the electric field oscillating on the x-axis, comes in, it hits the molecule, and then maybe comes out oscillating on the y-axis. So you have an x and a y symmetry multiplied by each other. So x times y will be a symmetry in that character table. I'll show you that in a minute. And then we use the direct product table from the point group to determine the symmetry of this transition dipole moment integral. So this is the procedure. Let's apply it. So, sorry, I went to the next slide. Some of you are still writing. So since we learn best by doing, let's do several examples of this. So this is a flashback to our particle in the box. Here's our energy level diagram. We only have one axis, so we really only have X, and only E and I symmetry elements. So here's our character table. You see, this is the CI point group right here. It looks like a C1, but there's a little dot on there, so that's a CI. It has the E and I symmetry elements. It has 2 rows, AG and AU. The G and U tell you the inversion symmetry. Notice when it's G, it's +1 under inversion. We say it's symmetric under inversion. And when it's U, okay, it's asymmetric under inversion. It's -1. That G and U are stand for German words, gerade, which is even, and ungerade, which is uneven. Okay, so that's where G and U come from. And so we can label those wave functions based upon their inversion symmetry. So if we went through this before, but if you invert each one of these wave functions, they either give you the same wave function back or they give you a -1 times that wave function. And so that's the +1 and -1 characters under the inversion operator. So here's our transition moment integral. You can see that we've found x in the table. And so since we have x there, that means that AU is in the middle here. So these are the symmetries. We have wave function 1 and 2. Let's just do that example down there at the bottom. So this x is AU right here. And we got that from the character table. That's why it's super important to get the point group right. If you get the point group wrong, you have the wrong character table. And you won't know, you will have the wrong symmetry for X, wrong symmetry for Y, Z, wrong symmetry for the motions of the molecule. So everything really depends upon that point group. So it's an important thing. And unfortunately, I mean, when you get into those exams, if you get the point group wrong, then everything's wrong afterwards. So you can really focus on being good at assigning point groups. There's a whole lab dedicated to that this week. So you'll get a lot of experience assigning point groups and a TA to help you. Okay. And work together too. This is more of a fun lab. You get to build molecules together and talk about the symmetries and help each other out. So then once we get to this point where we have the symmetries, we have the symmetry of wave function 1 right here, the symmetry of wave function 2 right here, the symmetry of light. Then we use this direct product table right here. So that's what this is called, direct product table. How can you tell the difference between the direct product table and the character table? We have two types of tables. Look in the middle here. Well, there's lots of ways, but look in the middle here. These are not characters. They're Millikan symmetries. Whereas you look up here, these are characters. It's a character table. You see that? Also, look at the top here. These are symmetry elements, and these are not. Okay, so it should be obvious to you when you're looking at a character table versus looking at a direct product table. They both have the Schoenflies notation or the point group designation in the upper left-hand corner. So that's how you can tell which one you've got. But in terms of when I say use the direct product table, you got to know what a direct product table is. And it's the one that looks at the combination of all the symmetries. And so then we work this down pairwise. So AU times AG, we can go up here to the direct product table and we can look at that combination. So we have AU there, AG here, and so this is the multiplication of those two. So that gives us AU. So we simplify the integral a little bit, and now we have two terms instead of three, and then we do that last combination, AU times AU gives AG. And where the intensity is proportional to that integral squared, which is non-zero because that's the top row of the character table. And therefore the 1 to 2 transition is allowed. So this is a little bit of review, but review never hurts. So let's see if we can do this in a general form. Can we generalize this? Well, if all GUs to AUs are allowed, then all AUs to AGs are also allowed, because it doesn't really matter in any of our problems which order you do these in. And so therefore the selection rules are plus or minus 1, 3, and 5, because I can go up 1, I can go up 3. So this is a G to U here, AG to AU, and this one is also AG to AU. So that one's allowed. We can't do this, AG to AG, that's a no, because light is odd. We're going from even to even, and we throw an odd, X symmetry in there, and the result is going to be odd. So that's not allowed. And AU to AU is not allowed because we have 3 odds. Remember, the odd even multiplication rules really do follow like the plus or minus 1 rules. So if we have 3 minus 1s, the result is going to be minus 1. So the result is going to be odd. And so that won't work either. So we can't go from U to U. So that one's not allowed. So we can have these selection rules, plus or minus 1, plus or minus 3, plus or minus 5. And that's for absorption or emission. So all these arrows could go down as well. Anything I can clarify at this point? We'll do scattering next. So I want to pause here just to make sure you're clear on every step. Okay, let's go to the scattering. So scattering uses the x squared operator. So you come over here, and in our system, we only have the x-axis. So the x squared is the only way we could scatter. We don't have xy because there's no y. We don't have xz because there's no z. Certainly don't have y squared or z squared. So it's very simple for a particle in a box. That's why we study it. And so here's our x squared, and x squared is even. So we make up, and also scattering involves light between the energy levels. So we typically draw this dashed line. And so what we want to know is if light comes in that doesn't match an energy level, can it scatter? So you see the incoming light goes up to that dashed line, and then the scattered light goes from that dashed line down to an energy level. We have to leave the molecule in one of its energy states. It can't be between the energy states. Light can be between the energy state, but a molecule can't absorb to that dashed line, but it could scatter. It could interact with that light and take some of that energy away from the photon of light and scatter off a smaller photon. So that's what's going on here. This is called inelastic scattering. And so we have psi 1 is the initial state, psi 2 is the final state. So that's n and n prime. And x squared is this scattering interaction, 2 photons of light. And so we set up the symmetries, AG, AG, and AU. So we go to our direct product table. AG times AG is AG. So we bring the AU down, and then we have AU times AG is AU. So therefore, the scattering interaction cannot drop the molecule or bring the molecule up one level. It's not allowed by symmetry. So we call this forbidden by symmetry. So we have scattering selection rules that are different than the absorption selection rules. So let's see what is allowed. So if the final state is AG, then that's allowed by symmetry. So the 1D particle in a box scattering selection rules can go from G to G, and honestly, they can go from U to U. Anything that matches initial and final state, because light is even. So as long as it's going AU to AU, that's similar to having 2 minus 1s. They're going to cancel each other out. So we have plus or minus 0, plus or minus 2, plus or minus 4. These are our scattering selection rules. And so plus or minus 0 is interesting. The molecule is unchanged, so we call that elastic scattering. So light comes in and scatters off at the same frequency, but it's at a different direction. So it interacted with the molecule or atom or ion or electron and comes in, interacts with it for a little bit. That's what the dashed line is. It's oscillating, and then it comes off at a different angle. So we call that Rayleigh scattering. If it leaves with less energy, it might go from state 1 to state 3. So that's a jump of 2, and that's inelastic scattering. We call that Raman scattering. So 2, 4, 6, 8, so on. That would be Raman scattering. Any interest? I mean, anything I can clarify on this? Okay. Why do we have a different selection rule? What was the main thing that changed here from absorption? You can look back at your notes. Compare these two cases, and what was the thing that changed? Or energy levels didn't change. The symmetries of those wave functions didn't change. It looks like we did the same procedure, so the procedure didn't change. What's different between this slide here, and let me go back through all the animations, and this slide here? This would be a good one, yeah. So this slide, we have different selection rules, plus, minus 1, 3, and 5. And on the Raman and Rayleigh scattering slide, we have plus or minus 0, 2, 4, 6, etc. What's the one thing that's changed between those two situations? Yeah, but what's the one thing? You're saying that one of the ones, like, be specific about the one. What's the one thing? The symmetries are different, yeah, in the middle. But what is that middle thing? Light. That's the interaction of light. We're talking about two different types of interactions with light. One is absorption and emission. The other is scattering. Okay. And that's all. That's the only difference. We have different selection rules because we have different interactions. Okay, so absorption and emission is one type of phenomenon. Scattering is a totally different type of phenomenon. So it's natural that they would have different selection rules. They're going to interact differently with those waves. And we can determine that using the symmetries of those interactions. So absorption and emission is just X or Y or Z. Just a single one of those. We call it order 1, right? Raman and Rayleigh scattering is second order. There's two axes involved, an X squared, a Y squared, a Z squared, an X times Y, or an X times Z, or a Y times X. So those are the interactions of the photons that come in. I'd like to think of it coming in on the X-axis and leaving on the Z-axis. That would have the symmetry of XZ, which is right here. Or if it comes in on the Z-axis and scattered out of the Z-axis, that would be the Z squared. And now in this character table, it's super easy. They're all in one row. But in other character tables, they're on all different kinds of rows. It's like in benzene, they're all on their own row. And so you have all these different types of interaction, whether it's a Z squared or an X, Y, etc. So that's part of the thing that's different in all of these different molecules is how light interacts with the molecule. But it's the same procedure, it's the same skill. And that's what makes it easy. It's the same procedure for each one of those. Let's do some other phenomena like rotation and vibration with water and some electronic excitation. So here's some molecular orbitals. This is in ammonia. And so this is the highest occupied molecular orbital and the lowest unoccupied molecular orbital. And these are the symmetries of those two. And so we want to ask the question, is light allowed to absorb the transition from HOMO to LUMO? So can we take those electrons in that cloud that are oscillating up and down and change them to this strange oscillation where they're oscillating inside and outside that nitrogen atom? And so can this one occur through direct absorption? We have two types of light now. We have Z polarized light, which is A1, or XY polarized light, which is E. Can I get you to close that door for me, please? Yeah. So we have initial state and final state, but now even in absorption, we have two types of light. We have Z polarized light and we have XY polarized light. So this is the symmetry set up. Notice the initial and final states are both A1. So these are, initial and final states here. So I'm just going to take these up and bring these over here. So these are right there and right there. Those always go on the outside. So we're going from one to the other, and the thing in the middle is light. So the light is always in the character table. We have Z here and XY here. And so here's our direct product table. Now this one is a little different. It's got some new features. The point group up here in the top has got a whole bunch of point groups. And that just means that this same table applies to C3V, D3, D3D, D3H. And so we can apply this table to multiple point groups. We have the symmetries down the left and across the top, but look at this one. When E is times E, we get 3 elements in it, okay? But one of those elements is A1. So that's why when I say, does it contain the top row, that would be a situation where it contains the top row, okay? So now let's do those multiplications. So does this HOMO to LUMO transition with light equal 0 or not? So for Z polarized light, we have A1 times A1 times A1. So all of those, it's just this thing repeated over and over again. A1 times A1 is A1, and A1 times A1 is A1. So the result of all three of these multiplied by each other is still top row, which that integral is not equal to 0, so this one is allowed by symmetry. The next one is XY polarized light. And so we look up here, E times A1. So in the direct product table, we have E here and A1 there. And so this is E times A1 is E. And then we do that again, E times A1. So I've just sort of done a shorthand. I've taken that result and drawn a bracket right here. So take it, E times A1 is E, and then this bracket is E times A1, which is going to be E again. And so that's our resulting integral. It's not the top row of the character table. So this one is going to equal 0. So this one would be forbidden by symmetry. So the result of the direct product is E for the XY polarized light. But the HOMO to LUMO transition is still allowed, but it's only allowed for Z polarized light. So if you've got this molecule, this ammonia molecule in space, and light's coming at it, the light that's polarized horizontally will not cause that transition, even if the energies match. So really only 1/3 of the types of light coming at this molecule can be absorbed. That will impact the intensity. So the intensity will be smaller to some degree because only 1/3 of the types of light coming at this molecule will be allowed by symmetry. Let's look at some rotational motion. So this is the energy level diagram for rotation. We haven't covered rotation very much, but I'm just throwing this at you. It's sort of a foreshadowing for what we'll do later in the class. These are the quantum numbers. So we have the quantum number J, and notice it's kind of a weird equation. It's J times J plus 1. That's just a traditional way to write it. So it goes up as J squared plus J. So it's not equally spaced. Also, the rotational energy levels alternate. Okay, the symmetry of the rotational motion alternates. The even quantum numbers have the top row of the character table symmetry, and the odd quantum numbers have the symmetry of the motion. So notice that B1, so we're talking about RY in water would be B1 symmetry. So that would be the symmetry of the motion. So the levels alternate, A1 to B1, then back to A1, then to B1, and so on. And so here's our B1, our rotation around Y. You see R, Y. We can go find that in the character table just to show where that B1 came from. So do you see that? RY is on the B1 row. So that's the symmetry of that motion. So that's how we knew that every other energy level was B1 and not B2 or A2. I went ahead and filled out this character table with all, normally they're shown in triangular form, but I went ahead and filled out everything just so you can see that it's symmetric. And so can this rotational mode be excited by light? This is the point group, C2V. We have the character table, the direct product table. The ground state wave function is A1. The excited state wave function is B1. And for the other rotations, like Rx is B2 and RZ is A2. So let's look at the Z polarized light. So we come in here and Z polarized light is A1. And so we can look at A1 times A1 gives us A1, and A1 times B1 gives us B1. So that's not the top row, so that one's going to be 0. So it's not allowed. This particular motion around the y-axis is not allowed with Z polarized light. Okay, here's X polarized light. So it comes in, it has the symmetry of B1. And so A1 times B1 is B1, and then B1 times itself is A1. So that one's not equal to 0. And so that's allowed. So that's great. We have X polarized light can cause that rotational transition. Let's try a vibrational motion. So here's the vibrational wave function. I talked about this a while ago too, how the quantum number is V, but the vibrational frequency is nu. So this is the quantum number V. And so they're listed over here, the V quantum number. Notice they start in 0, 1, 2, 3, 4, 5. So they go up. And then this is the vibrational frequency. These alternate as well. They go from A1, which is top row, to the symmetry of the motion, and then back to top row. So the asymmetric stretch is shown on the right. So let's look at the symmetries of this one. So the asymmetric stretch is B2 because it has the symmetry of Y. Remember we did our cancellation of the component vectors to determine that the Y motion in this symmetric stretch was the symmetry that we needed to look up. So we come down to the character table and we find the symmetry of that Y motion, and then that's how we know it's B2. So that's going to be that upper state, that symmetry of the Y motion is going to be B2. And then we look at light. So Z polarized light is A1. So we have the ground state A1 times light, which is A1, and then that interaction times the Y symmetry of this asymmetric stretch is going to be B2, and that's going to give us B2. So since that's not the top row, that's equal to 0. So it's forbidden for Z polarized light. This vibrational stretch with this asymmetric motion in water is not going to be excited if Z polarized light comes in. And that kind of makes sense, right? Because the stretch is moving kind of in the Y direction, and if light is oscillating in the Z direction, they're 90 degrees to each other. So it's not really going to interact. What will interact is Y. If the vibrational motion is in Y and light is polarized in the Y direction, naturally they're going to interact. And so we have the symmetry breakdown for this one. The A1 times the symmetry of light. So there's two Y's here. The bottom one is light, and the top one is the symmetry of the motion. And this first one is ground state. So you see where all three of those pieces come from. We use the character table to assign their symmetries. So Y is B2. So A1 times B2 is B2, and then B2 times itself is A1. So this one is not equal to 0. And it's that simple. Okay. So that's all that's prepared for the notes. Let's go up and do one of these where it's really complicated. So let's look at this direct product table here. And I'm going to show you one that, let's see, let me erase this stuff here. What if in ammonia we had some orbital, I don't know, let's see, let's say we had an orbital that was like this, and let me pick another one. One where there was maybe a node in the back. I mean, a lobe in the back and a lobe in the front. But the point is, if you don't like my pictures, we're just saying we're going from E to E. This is the most complicated case, okay? So we've got E in the lower state, E in the upper state. Don't worry about the pictures because it's hard to draw, okay, by hand. Okay, and we want to know if this is allowed by Z or XY. Okay, let's look at this one here because that's the most complicated one. That's E. So if we have the situation where we have E times E times E, this is the messiest one we can do. Okay. So what would we do with that case? We come up here to the direct product table and we look at them in pairs. We have E times E. So that gives us a set. It gives us a set that, you know, in this little set language, you can put a little curly bracket, A1 plus A2 plus E. And now I have that first E times this whole set. Well, just think about in algebra. If you have, say, X times Y plus Z, you have X times Y and X times Z, right? The X goes through and multiplies by each one of those pieces. So it's not that difficult. You have over here now the result in my integral. I'm going to draw this first bracket pretty far over here. And I'm going to say E times A1 gives us this first term, right? So what is E times A1? E, thank you. People are out there. Okay. What is E times A2? Boom. So it hits this one. It comes over here. So it's E again. Plus, and then E times E gives us this set again. A1 plus A2 plus E. And what am I looking for in all of this? So this is an enormous integral. If you were to really do this with the functions, it would not fit in this room. Like you couldn't write it out on these boards probably. It would be so big. But we know what the symmetries are. And so this big, huge first term, the symmetry would be E. And if I integrated that over all space and evaluated it at the limits, then it would end up being 0. And we know that because the symmetry of that first piece is E. The second piece, the symmetry is E, also 0. The third piece is symmetry is A1. That one's going to be non-zero. So we have this piece right here is A1. We know that's top row because we look at the character table for C3V. And so this is the one right here that's non-zero. And so we come over here and we say not equal to 0, therefore allowed. Okay. And that's about the worst one, is 3 E's times each other. Maybe not the worst one you'll see, but that's the worst one you've seen so far. And it's not that bad. Okay. All right. Well, y'all have a good day. We've done all three, and we've determined the selection rules for some really complicated stuff. Enjoy the lab, making molecules and determining symmetries, and work on your drawing. Okay. Hopefully you're better than me.